Welcome back to The Explainer, everyone. Today we're diving into an absolute breakthrough in robotics that is fundamentally changing how we talk to our machines.
Okay, let's just get right into it. You know how artificial intelligence can write complex code, it can pass the bar exam, and it can generate photorealistic art in seconds, right? Well, if you ask a state-of-the-art robot to do something as basic as grasping a toy mushroom, things get surprisingly messy. We have these incredibly brilliant digital minds, but actually putting them into physical bodies, that remains one of the hardest challenges in modern science.
Consider this exact setup from our source material. You've got a Widow X robot arm hovering over a desk, and scattered around it are a bowl, a spoon, an unusual toy hammer, a plate, and a toy mushroom. Now, if we tell this robot to put the hammer on the plate and pick up the mushroom, it completely fails. It fumbles around, it grabs the wrong thing, it just doesn't work. Today, we're going to unpack exactly why that happens and how a really fascinating new algorithmic framework called SARL actually fixes it.
Here is our roadmap for today's explainer. We'll cover 1. The generalist robot problem. 2. Why direct prompting fails. 3. Introducing semantic action RL. 4. The VLM and RL loop. 5. Real-world robot results. And finally, 6. The future of adaptation.
Let's start with Section 1, the generalist robot problem. Currently, the absolute gold standard in the field relies on vision language action models, or VLAs. Think of a VLA as a massive generalist brain that's been pre-trained on a huge amount of human teleoperated robotic data. This pre-training is designed to give the robot a general sense of how to move its joints when it sees an image and receives a language command. In theory, it seamlessly transforms what it sees and what you tell it directly into physical robotic actions.
But here's the catch. When we give a VLA a long, complex command that falls just slightly outside its standard training, like dealing with a highly specific multi-step setup with an unusual hammer, it hits a brick wall. The generalist brain just can't seamlessly break down the semantics of a complex, long-horizon task into atomic, executable physical behaviors. It knows how to move, sure, but it doesn't know how to sequence those movements for a brand new, multi-step problem.
Moving to Section 2. Why direct prompting fails.
To really understand this failure, we have to contrast two different ways of controlling a robot. Historically, if you wanted to build, say, an omelet-making robot, older reinforcement learning optimized low-level robot actions. We're talking about mapping out precise motor torques, exact wrist angles, and joint positions. It is incredibly tedious. Modern VLAs, on the other hand, try to use semantic actions, high-level language commands like turn on the stove or grab the egg. This is obviously a huge leap forward, but as the researchers point out, these models get profoundly confused if the semantic command is just a bit too complex or involves objects they haven't seen much before. Just look at what happens when researchers gave a naive prompt, literally telling the robot to move the out-of-distribution hammer to the plate. The robot got completely overwhelmed by the complexity of the instruction. Instead of grasping the hammer, it hilariously reaches out and grabs the spoon instead. It fundamentally misunderstood how to map the language of the prompt to the physical reality of the object sitting right in front of it. Which brings us to Section 3, Introducing Semantic Action RL. Enter SARL, which stands for Semantic Action Reinforcement Learning. SARL takes a radically different approach to robotic training. It stops trying to train the robot's physical motors or tweak its joint angles. Instead, it runs an online reinforcement learning loop over the language prompts themselves. It treats the language instructions as the action space, using real-world interactions to learn exactly which specific words and phrases will actually compel the robot's pre-trained brain to complete the task successfully. So instead of feeding the robot a massive, naive prompt that just causes it to panic, SARL figures out that a sequence of simple, grounded commands works best. It achieves two incredibly vital things: decomposition, meaning breaking down complex goals into bite-sized stages, and grounding, tying those prompts to physical truths. For example, instead of naming the unusual hammer, SARL might just discover that telling the robot to simply move down and grasp works perfectly. It anchors the language to physical reality without confusing the robot's vision system with object names it might misinterpret.
Section 4, the VLM and RL loop.
Here is the three-step magic that makes this whole system actually hum. First, a vision language model, or VLM, looks at the camera feed and proposes a list of candidate semantic prompts based on what it's seeing. Second, SARL's specially trained Q function acts as a filter, essentially a mathematical scoring system, selecting the absolute best prompt from that list to try out. And third, the robot physically executes the action and receives a reward based on whether it got closer to the goal.
It's this continuous, self-improving trial and error loop happening right there in the semantic space.
The source text gives us this fantastic quote. By grounding prompts in real-world experience, we can efficiently refine which of them actually lead to success. You see, while standard language models are incredibly smart, they totally lack physical grounding. A language model might confidently tell a robot to drop a piece of sushi a bit too early because, hey, it makes sense in text, but it completely fails in actual physics. This SARL loop ensures every single semantic action is strictly tied to a successful, tested, real-world consequence.
Section 5. Real-world robot results. The sheer efficiency of SARL boils down to a remarkable number, less than 100. It takes fewer than 100 episodes of physical trial and error for the Widow X robot to adapt to complex, long-horizon real-world tasks. In the world of robotics, where training traditional models can sometimes take millions of simulated steps or thousands of human demonstrations, adapting dynamically in under 100 physical episodes is just staggeringly fast.
And the performance data backs this up. SARL easily achieves up to an 80% success rate on these complex real-world tasks. Older motor action-based methods completely fail here. They just flatline. They get trapped trying to fix bad micromotor movements, exploring a narrow funnel of joint angles. SARL, on the other hand, succeeds by simply stepping back, rewriting the prompt, and accessing the skills the robot already has hidden inside its pre-trained brain. This breakthrough really comes down to solving two distinct failures of prior methods. Basically, older methods either explore motor actions but lack language-based exploration, meaning they can't decompose a task, or they explore language but completely lack physical grounding, meaning they suggest actions that look great on paper but totally fail in gravity. SARL is uniquely powerful because it combines both. It explores language to break down the task, and it uses reinforcement learning to ensure those language commands are actually grounded in physical reality.
And finally, Section 6, the future of adaptation. The ultimate takeaway here is moving away from the failure of naive prompting, where we just shout a complex command at a confused robot and hope for the best. Instead, by feeding the robot small, grounded, bite-sized instructions like move down and grasp, SARL essentially learns how to speak the robot's own internal language better than we ever could manually. It acts as an automated translator between our high-level desires and the robot's actual physical capabilities. Which leaves us with a pretty fascinating thought to take away. If robots learn to navigate the physical world fastest by having AI algorithms rewrite their internal language prompts, what does that mean for how we'll program the physical automation of tomorrow? If the secret to physical automation isn't just building better hardware, but rather teaching AI to speak a better internal language to itself, how will that change the robots in our homes, our hospitals, and our factories tomorrow? It is an incredible paradigm shift away from manual programming and toward semantic guidance. Thank you so much for joining me on this explainer, and I hope this provided a clear window into the cutting edge of robotics.